Hello, my name is Zichen, and I'm a PhD from Boston University. I'm happy to present our work here, Mnemosyne dynamic workload-aware Bloom filter tuning via accurate statistics in LSM trees. This work was accepted by SIGMOD 2025, and it is a joint work with Yanpeng, Hyoung, and Manos. Log structure merge tree, short as LSM-tree, has been widely adopted in many databases because it offers fast ingestion rate and competitive read latency. In LSM-tree, most of data will be stored on disk, and the data will be organized by level. Each level is essentially a sorted run, and the capacity of each sorted run will grow by a constant factor t. To accelerate point lookups, LSM trees maintain two meta structures, Bloom filters and fence pointers. Bloom filter is a bitmap that can help us determining if the queried key belongs to the sorted run or not, with low false positive rate. It has a bit per key parameter that controls the trade-off between the space and the accuracy. The fence pointer is a list of the minimum key and the offset of each data block. It ensures that at most one data block will be used to answer a point query in a sorted run. Let's now look at one example to see how these structures are being used in this query procedure. Suppose that we're querying the key k. We'll first look it up in the write buffer, and if we cannot find it, we'll traverse the LSM tree in a top-down manner. When we query each level, we'll first query the Bloom filter first, and if it says no, we move on to the next level. And we will do the same thing. We'll query the Bloom filter first. If it says yes, we'll move on to the fence pointer, and the fence pointer will tell us the exact data blocks that may contain the key. We may retrieve that data block from disk, may find no matching key because of the false positive rate. And if that happens, we move on to the next level. We go through the same procedure as I mentioned earlier, and we go to the retrieve the data block. We find the matching key value pair. We return the associated value. In practical implementations like RocksDB and LevelDB, each sorted run will be implemented as multiple sorted string table files, short as SST files. In such implementations, when users specify the bit per key for the entire LSM trace, the same bit per key will be used per file to build the Bloom filter. However, if we look at the access frequency patterns by looking at the CDF of each SSC file, we'll find that even in a perfectly uniform workload, 80% of the lookups are directed to just 45% of the files. And this is because files in shallow levels naturally have higher access frequency than files in deeper levels. Assuming the min-max range is approximately the same across all of the levels, as the number of files grow exponentially, the min-max range becomes narrower when we are moving to deeper files. Inspired by this, we allow different files to have different bits per key, which can help us exploit these access frequency patterns. Different bits per key, in other words, we allow them to have different false positive rate. And let's see how we achieve this. We are trying to solve this optimization function, and then we get the best false positive rate, essentially the best bits per key per file. Here, the capital F represents the number of files in total, and the I represents the number of empty point lookups for file I. Epsilon I represents the false positive rate for filter in file I. The term we are minimizing here represents the number of unnecessarily triggered IOs from filters. And in the constraint, we require the total space occupied by a filter should not be larger than a fixed memory budget, M. The G function takes two parameters, epsilon I, the false positive rate, and the Ni, the number of key value pairs in file I. Depending on different filter implementations, we could have different G function. Note that we here do not strictly require this filter to be a Bloom filter. It could be Bloom filter cuckoo filter, or even a ribbon filter implemented in RocksDB. In either definition of this, when we plug in the G function, we will show that G function remains convex. And because of that, we can always use gradient descent to find out the optimal bits per key or the optimal false positive rate per file. Compared our model with one of the state-of-art academic model, Monkey. Monkey also tries to minimize the number of unnecessarily triggered IOs, but it assumes uniform access distribution. And that's why in the objective function, you do not see any weight factor. It's just summing up the false positive rate across levels. Here, the capital L represents the number of levels. Before we even solve this monkey optimization problem, we could already imagine that because files in shallow levels naturally have a higher access frequency, files in shallow levels will have larger bits per key or lower false positive rate. But in our model, we do not necessarily have this guarantee, especially when the query workload becomes more skewed, because we have the ZI coefficient to control the access frequency. But is that all the difference between monkey and ours? Unfortunately, these two models are still very ideal. They cannot be directly deployed in real system because it relies on prior knowledge. Monkey needs to know the number of levels L in advance, and so does our model. We need to know the capital F, the number of total files, ZI, the number of empty point lookups per file, and so on and so forth. Let's look at the workflow of Monkey to understand this limitation. So this is a mixed workload that we are going to execute. And Monkey assumes that we kind of know this workload's knowledge in advance, especially for the inserts. We know the number of L approximately in advance, and we use that to build our optimization model. We compute the bits per key per level, and when we executing this workload, we follow this static bits per key list to build our Bloom filter when we construct the LSM-tree. And it turns out that if we do that, the average bits per key will be either overutilized or underutilized. Let's look at the dotted purple line, which represents the actual average bits per key for Monkey if we use the top-down insertion way to build the LSM-tree. The top-down way is the traditional way we build the LSM-tree. Files in shallow levels will be created first, and then files will be moved or compacted to deeper levels. If we can recall the results from Monkey earlier, we see that files in shallow levels will naturally have higher bits per key than files in lower levels. And that's why when we are digesting this workload, we will always have the overutilization issue at the beginning when we're executing this workload. Because the average bits per key is the same as the user configured one, files bits per key in shallow levels is always larger. And this overutilization will last until we digest most of the operations, and the number of levels become the same as the one we use to compute the bits per key list. From this example, I hope you can get a feeling that what we really need is the on-the-fly bits per key allocation scheme, and we do not want to overuse or underuse the user config bits per key. To achieve this, we propose Mnemosyne. We try to solve this optimization problem during each compaction. And as you can see from the dashed border box here, we have F prime, which represents the current number of files, and M prime, which represents the current memory budget. And we do not need to know the F and M in advance because we just solve this optimization for that state of our LSM-tree. But there's are still two challenges. The first one is the efficiency. How efficient it would be to solve this optimization problem. Recall that the median compaction latency is no more than 1 second in our earlier study. In our work, we show that there exists a fast solver based on dual theory, which can solve this problem very efficiently without introducing much overhead during compaction. The second challenge is that how to get the number of empty point lookups. In our work, we propose Merlin, a window-based tracking mechanism, which can provide more accurate statistics, which will be used to instantiate our optimization problem. Now let's look at our experiments. The first experiment compares our method, Mnemosyne, with 3 baselines, 2 versions of Monkey and the RocksDB. We will use a mixed workload has 26 million operations, which is mixed by inserts, updates, and empty queries. The upper figure shows the runtime throughput, and the lower figure shows the actual average bits per key. The green line represents our method, Mnemosyne. And as we can see, in the first 5 million operations, which are all inserts, there is no much difference between our method and all other baselines. And when there are more point lookups involved in the following operations, we see the green line shows higher throughput than other baselines. And at the same time, we also observe that the green line never overuses the user configured bits per key. So to summarize these 2 figures, Mnemosyne has higher throughput than RocksDB and Monkey without overusing the bits per key. In the next experiment, we only compare Mnemosyne with RocksDB. This is because in earlier experiment, we still assume Monkey knows the prior knowledge of the workload. We somehow faded this workload info to Monkey. But in real world applications, we cannot do that to feed some workloads information to the system because we do not know the workload in advance. That's why we only compare Mnemosyne with RocksDB. Here we vary the bits per key from 2 to 7, and we also vary the proportion of empty queries from 0 to 1. Here the query workload is still a mixed workload. It is mixed with updates and queries. The queries will be more skewed in this experiment, and we show the average query latency. As you can see, Mnemosyne does not need to have the prior knowledge, and it achieves much lower query latency for skewed access when it is compared to RocksDB. As a short summary of this presentation, Mnemosyne outperformed RocksDB by up to 36% without knowing prior knowledge of the workload or over-allocating memory for the Bloom filters. Thanks for listening, and feel free to check our full papers for more details.